Okay, so yeah, day 35, and today is November 15th. So today we're going to talk about random variables. We're sort of back on track. Assignment 4 has been released. It's up on Brightspace. I was thinking about this after. I'll probably release an updated version where it sort of each question points back to the lectures or lectures that you should refer to. But for now, it's up. You can get started on the first part, which is basically infinite sample space. All right. So yeah, any questions before we get started? Okay. So yeah, we're going to talk about random variables. So in some sense, we've already been talking about random variables. We just didn't know it. They are very useful. This lecture, we're going to go into a lot of technical details, and maybe it's going to be might go a little slow in points. We're going to solve a lot of equations. But random variables leads directly into things like expected value, which is very, very interesting. And then indicator random variables, which are also very interesting. They're interesting because they can solve a lot of problems for us, and they're also, in some sense, kind of easy, right? So there are tricks and proofs that we can use to make things like determining the expected value of some experiment sort of a very easy thing to compute. Okay, so, but to start with, talk about random variables. Okay, so of course, we've been talking about probability so far. So in probability, we have a sample space. There's an outcome, which is an element of the sample space. Each of these outcomes is mapped to some number between 0 and 1. Technically, this is a probability function. And if I sum up all of the individual probabilities, they sum to 1. And then there's, of course, events, which are simply subsets of the outcomes. So yeah, what is a random variable? Neither random nor variable, right? So whoever named this, I don't know, perhaps they had some other idea in mind, but they're not random, they're not a variable, they're a function. They're a function that takes some outcome and maps it to some value. And which value? Well, we get to decide. So we might be interested in certain outcomes and we might place a certain value on them, right? For instance, if I roll 2 dice, maybe the value I place on them is the sum of those 2 dice, right? Or maybe I'm in a casino, heaven forbid, don't go there, but maybe I'm in a casino and the sum of the roll of the two dice is mapped to some, winnings or losings. But yeah, so we already saw when we talked about 2 dice, rolling 2 dice, we sort of informally talked about random variables. So technically, the sample space on rolling 2 dice consists of a pair of values, right? So I is my first die, J is my second die, and IJ represents the 2 values of those dice. Okay, so then we can apply a function to all of those elements in the sample space, and we can define this function however we like. In this case, we can define it as perhaps the sum of the 2 dice, right? That's really a very, very natural way to define. My outcome is by, well, I roll 2 dice. Yes, I am sort of interested in the individual die rolls, but I'm probably a lot of the time interested in the sum, right? The sum is going to determine some outcome for me. So I can define my random variable x is a function that takes an outcome, in this case, I and j, and produces some value, maps it to a value. Yeah, so in this case, I roll my 2 dice. My function, my random variable x, maps those 2 dice, 2 and 2, to the value 4. Okay. So we typically describe these random variables, so we can actually list them out, and we will do that, but typically we describe them in English, right? The same way we We describe events. We sort of often do it informally. In this case, the random variable X is the sum of my two rolls of, fair six-sided dice, if I wanted to get specific. And when we talk about random variables, we don't often write them out like this, although we can, right, if we want to sort of be very, very specific. But most of the time, we'll just write X, and then we'll know that X maps to some value. Okay, so let's say we perform an experiment where we flip a fair coin 3 times, right? And then I can list out all of the outcomes in my sample space, which is all of the ways I can get heads and tails on 3 flips. So there's 8 outcomes in my sample space. And then I can define a random variable X. Again, I can define it however I like. So I'm going to define it as the number of heads in my 3 flips. And yeah, so if I wanted to, I could define it explicitly, right? So this is okay. But just to get a sense of the entire, I guess, domain of this function, I could list out each outcome explicitly and what value it maps to. Right. So this is my random variable X. This completely defines it. This entire mapping is essentially the same as saying this, right? Okay. And then I can define a second random variable on the same experiment on the, on my same sample space S. I can define this random variable Y equals 1 if all 3 flips are equal and 0 otherwise. Okay, so then if I wanted to map all of these explicitly, well, if I flip all 3 heads, then all 3 flips are equal, so Y maps to 1. If I have 2 heads and 1 tail, then of course Y maps to 0, and so on and so forth. All right, so really, Y really only has 2 outcomes that map to a value other than 0. These 2 outcomes map to 1, and everything else is 0. So these are legitimate ways to explain or describe a random variable, but we usually stick to English as it's easier. Okay, so I have my X, my Y random variable. Question so far? Yeah. Oh, did I mess it up somewhere? Yeah, that's a typo, yeah. That's one of those ones, every semester somebody points it out and I always forget to fix it. But yeah, that should be a 2. Yeah, other questions? Okay. Okay, so now, now I can describe events using my random variables, right? So how do I describe these events? Well, an event is just a subset of the sample space, and each of the values that I map my random variable to is in some sense associated with a subset of the sample space, right? So for example, I can describe the event my random variable X is equal to 0. And what is that? Well, that is basically all of the outcomes for which my function X gets the value 0. In this case, it is the outcome that I flip all 3 tails. The event X equals 1, there was 1 head in my 3 coin flips. Well, again, I can say, well, I'm going to collect all of the outcomes together that when that my function X maps to 1 for, basically. So in on the previous slides, we looked at taking an outcome and mapping that to a value. Now we're taking a value and we're mapping those to the outcomes. Okay, but yeah, so those are all of the outcomes that give us X equal to 1, X equal to 4. There were 4 heads in 3 coin flips. That corresponds to the empty set, right? So this event could not possibly happen given this experiment. For event y equals 1, all three flips are equal. I have heads, 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 or tails, tails, tails. And event y equals 2 is, of course, the empty set. And y equals, well, we'll get to that, I think. Yeah. So if I listed out all of the possible events associated with all of the non-empty events associated with my random variable x, I have x equals 0, x equals 1, x equals 2, and x equals 3. Each of them maps to some outcome, or, in some sense, that outcome maps to that value. And I can do the same thing for y. I can list out all of the non-empty events associated with my random variable y. So y equals 0 is associated with all these outcomes. And y equals 1 is these two outcomes. So now I've defined all my events, non-empty events that are associated with y and x. Okay. And these are just events. The same events we talked about, in the past lectures, we talked about event A, event B, all of those things. Now we're going to talk about event x equal to k, but it's the same thing. It's just some subset of the sample space. And so, yeah, I can define it using the set builder notation. It's all of these elements omega such that x maps omega to the value k. Right, so S is my sample space, and then this is some set of real numbers that my function x maps to. Then the event x equals k is simply all of these, since all of those get mapped to the value k. Okay, so it's just an event. Same as all of the events we've been talking about before, we're just describing it a little bit differently using random variables. All right, questions? Okay. Like any event, if I want the probability of this event, probability that x equals k, I look at all of the outcomes that are in this event, and I sum their probabilities. Okay, so again, exactly like every other event that we've looked at. So my probability that x equals 0 is equal to the probability that I get 3 tails, right? And so I skipped a lot of steps, but this is a uniform sample space, and I can take the size technically if I wanted to get, since this is a uniform sample space, I can take the size of this event x equals 0 over the size of the sample space, which is 1/8, right? So that's what I'm doing. I skipped all those in between steps, but that should be hopefully pretty clear at this point. My probability of x equals 1, again, well, now the size of this event is 3. The size of my sample space is 8. So I have probability that x equals 1 is 3/8. Probability that x equals 2 is also 3/8. The probability that x is equal to 3 is 1/8. So just all heads. And of course, every other value for x is empty, right? So it has a probability of 0. So only the non-empty events have probabilities. And if I sum them all up, if I take 1/8 plus 3/8 plus 3/8 plus 1/8, I get 8/8, which is 1. Okay, so every single outcome must be mapped to a value for a random variable. And if I look at all the non-empty events defined by the values of those random variables, the probability should all sum to 1, right? Completely describes the sample space. I can do the same thing with my random variable y. Y equals 1 is equal to the probability that I get tails, 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 or heads, 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 It has a size of 2 over my sample space, which is a size of 8. I get 2/8 or 1/4. And the probability that y equals 0 is, of course, 6 over 8 or 3/4. And again, if we add these up, since these are the only two non-empty events, they sum to 1. In this case, since we have this random variable y only describes 2 events, we can use things like the complement rule, right? So the event y equals 1 is the complement of the event y equals 0 in this case. So I could have computed the probability that y equals 0 directly using the probability that y equals 1 and the complement rule. Okay. Okay, we can, yeah, questions so far? Yeah, I think this is kind of going to be a bit of a dry lecture, I think. We'll try and do some interesting problems at the end. So I can define another event based on my random variable. It doesn't just have to be equality. I can do things like inequality, right? So x greater than or equal to 2. Well, that is, I have at least 2 heads in my 3 flips, which is heads, 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 tails, heads, tails, heads, or tails, heads, heads, right? So I could describe this in English, at least 2 heads in 3 flips. Yeah, and then the probability of this event, at least 2 heads and 3 flips, or, you know, or x greater than or equal to 2 is 4 over 8. It's the size of the event over the size of the sample space. So it's probability 1/2. We could also break it down into cases, right? X greater than or equal to 2. Well, the only 2 non-empty events that fit this description are x equals 2 and x equals 3. They are disjoint, right? I can't have an outcome in 2 different. I can't have an outcome with 2 heads and 3 heads at the same time. Since they're disjoint, I can simply use the sum rule. So yeah, probability that x is greater than or equal to 2 is the probability that x is equal to 2 or x is equal to 3, which also gives us 1/2. Okay, questions? Okay, so that's our random variables. We can assign them any values we want based on the outcomes. They're functions, right? I give you an outcome in a random variable x, and that will give you back some real number. And I can define events on those real numbers, or sorry, on those functions by sort of mapping backwards, right? I take some real number that it maps to, and I say, well, give me every outcome that's associated with it. And that describes an event. And then I can have 2 events, right? Remember from events that we can have 2 events and we can describe them as being independent or not independent, right? So, and how we proved that 2 events, A and B, are independent is that we took the intersection, the probability of the intersection of A and B, and if that was equal to the probability of A times the probability of B, then they're independent, right? That means that, and if they're independent, that means I perform an experiment, I tell you event B happened, and you have no extra information about the probability of event A happening. Okay, so given that random variables can describe events, we can describe this notion of 2 random variables being independent or not being independent, right? So what that means informally is basically the same as our other events. If I tell you that I perform an experiment, I have random variables x and y, and I tell you x is equal to k. And then none of the probabilities for your events in y will change. The ones in x will change, of course, because if x is equal to k, then it can't be equal to, for instance, k minus 1. But if I tell you x is equal to k and you have still no other So whatever the probabilities of your events in Y are, those all stay the same. So I tell you X equals K and you have no good guess as to the value of Y, or no better guess, then they're independent. And yeah, that works both ways, of course. If I tell you the value of Y, of course, now I've ruled out all the other values of Y, but in terms of what X could be, it could still, all of those still have the same probability. So yeah. The probability that X equals K, again, that's an event, given that Y equals L is still equal to the probability that X equals K, and this holds true for all values K and L that are non-empty. Okay. So yeah, formally random variables X and Y are independent if for all K and all L, the events X equals K and Y equals L are independent. Yeah, and of course, how we prove they're independent is that the probability of the intersection of the events X equals K and Y equals L is equal to the product of the individual probabilities. All right, we just use the same old formula. We're just describing events a little bit differently. But for two random variables to be independent, this has to be true for all values K and L, which means that we have a whole bunch of these, potentially a whole bunch of these to prove that two random variables are independent. Okay. So often if I ask you if two random variables are independent, there's going to be two possibilities. If they're independent, there's going to be a lot of symmetry and you'll be able to do all these equations really quickly. Or you're going to say, well, they're probably not independent. And I'm going to prove that. So to prove that they're not independent, I would take, so this is sort of the formal logical statement of X and Y being independent. So I'm going to, using logic, I'm going to negate it. If I negate it, then using the rules of logic, I flip these. These are, oh my goodness, 1805,
Yes.
So long ago. Well, they're quantifiers. These are, what do they call them?
Sorry?
What kind of quantifiers? I forget. What's that? Is that what they're called? Universal? Okay. I wanted to call them that, but I felt like that was wrong. Okay, so universal quantifiers. These are the for all, and these are existential quantifiers. These are there exists. Okay. So yeah, using formal logic, the negation of this is that there exists a K and L such that the events X equals K and Y equals L are not independent, right? And so what we're saying in English is that to prove that X and Y are not independent, I just need one counterexample. I don't need to prove all of the cases are not true. I just need one to be not true, right? So we have to prove that they're independent, I need to prove they're independent, I have to prove that these are equal for all possible values. But to prove they're not independent, I just need to find two values, K and L, for my random variables X and Y, such that this is not true. And then I'm done. I don't have to do any more work after that. Okay. So we'll see an example, but any questions so far? Okay. All right, so back to our original random variables X and Y. X is the number of heads in 3 flips, and Y is 1 if all 3 flips are equal, and 0 otherwise. Are they independent? So who here has understood anything I've said so far? What's the guess here? It's hard. It's 8:30 in the morning. I don't blame you guys. Yeah, so we'll go through an example and we'll see. Are they independent? And what that means is that if I tell you something about Y, would I now know something about X? Okay, so X, if I look at all the sort of non-empty events, then K has these values, 0, 1, 2, and 3. And if I look at Y, all the non-empty events, Y has those two values. So that means I have 4 events in X and 2 events in Y. And I have to look at all combinations, so I have 8 of these equations I should verify. Right? So if I wanted to prove that X and Y were independent, well, then I have to take X equals 0 and Y equals 0. Those are 2 events. I have to prove that those 2 events are independent. And then I'm going to say, well, I'm going to stick with Y equals 0 for a while and look at all possible values of X. So X equals 1 and Y equals 0. Those also have to be independent. Y equals 0 and X equals 2. Those also have to be independent, and so on and so forth. So, Y equals 0 for each, for Y equals 0, I look at every possible value of X, and then for Y equals 1, I do the same thing over again, right? It's as if I run 2 nested for loops, one from 0 to 3 and one from 0 to 1, and then take all combinations. So I have 8 of these to verify. And 8's not bad. I could do that. There's way worse, of course. But let's think about this. So if I tell you something about Y, does that tell you something about X? Right, so if I told you Y is equal to 1, all 3 flips are equal. Do you now know something about the value of X yet? Right, exactly. So if I tell you that Y equals 1, that all 3 flips are equal, then I know the outcome was, not X, was either heads, 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 or tails, tails, tails. And if I look at the possible values of X, then X can't be 1, right? Because I know that there was not just 1 heads, there was either 3 or 0. X can't be 2. So yeah, X is either 3 or 0. So yeah, if I tell you Y, I've given you information about X. So that is the intuitive way to, that's going to give you the hint to tell you that they are not independent. You still have to prove it. But yeah, so this is basically what we just talked about. If I tell you Y equals 1, then the event is in, these 2 outcomes. And then we must have X equal to 3 or X equal to 0. X equals 2, we know that the event is in these outcomes, and then we know that Y must be 0. So I tell you something about one of them, it gives you information about the other. So what I want to do then is I want to find a counterexample to this formula. Right? So I want to find values for K and L such that the probability X equals K and the probability that Y equals L is not equal to the probability X equals K times the probability Y equals L. The easiest way to do this, since these are non-empty sets, if these are non-empty sets, I know these 2 probabilities are not 0. Right? They have to be something other than 0. So I know probability X equals K is greater than 0, and the probability that Y equals L is greater than 0, which means that the product times probability Y equals L, it might be small, but it's also greater than 0, right? These are non-empty sets, so this must be true. That's not necessarily true of this, right? If I can find 2 events that contradict each other, that is, they have no intersection, then it's going to have a probability of 0. And that's sort of the easiest way to prove this is to find 2 events that cannot possibly happen at the same time. Okay. So yeah. So yeah, we want to find values K and L such that the intersection is empty. and if the intersection is empty, then the probability is equal to 0. So if I take k equals 2 and L equals 1, so again, L is associated with Y. That means that this is heads, heads, heads. And k equals 2 is, of course, heads, heads, tails, etc. All the ones with 2 heads. So these both cannot be possibly, there's no intersection here. So that means the probability that x equals 2 and y equals 1 is 0. And at that point, I'm essentially done. Although, if I wanted to be complete, I could look at the probability of x equals 2 and y equals 1. Again, they're not empty. I know they're greater than 0. So, but yeah, for completeness, we can go through all of the steps. Yeah. So x and y are not independent because I found a single counterexample. All right, questions? Okay. Okay, let's define another random variable z on the same sample space. Z is equal to 1 if the first flip is heads and 0 otherwise. It's nice and small. So we're going to ask if, well, we know x and y are not independent, but how about y and z, right? They're both small, so maybe there's going to be a small number of things we have to check. If they are independent, first of all, any guesses? So using your intuition, if I tell you something about x, does that tell you anything? Or sorry, if I tell you something about y, do you have extra information about z? I mean, nothing obvious comes to mind, for me at least. So let's test it out. Y and z each take on 2 non-empty values, right? So these, they have 2 events that are not empty. So I can have 2 events for y and 2 events for z. So I look at all combinations. There are 4 possible, intersections of events. So I can have y equals 1 and z equals 1, y equals 1 and z equals 0, y equals 0 and z equals 1, or y equals 0 and z equals 0. And for all of those pairs, I have to show that these are true if I want to show that they're independent, or I need to find one for which it's not true to show that they're not independent. So since we don't really seem to have any good intuition as to why they might not be independent, we can start proving them. Questions so far? All right. Like I said, this lecture is a lot of these types of equations. It's just sort of the nature of the thing. But the probability that y equals 1 and z equals 1, well, let's look at z. I really didn't define, but let's take a look at, right, I defined the probabilities for y equals 1. That is 1/4, right? Let's not reduce it. Let's write it as 2/8, because we know that this event has size 2 and the sample space has size 8. And the probability that y equals 0 is 6/8. What about the probability that z equals 1? So the first flip is heads. What's the probability of that? Yeah, it's a half. And we can look at the sample space and look at all of the ones where the first flip is heads. So I have 1, 2, 3, 4, and these are not, so I get 4/8. Since all of these coin flips are independent, I can also cheat, right? What's the probability that I flip one coin and get heads? It's 1/2. So I can just look at that. I can just look at a sample space consisting of the first flip, which is either heads or tails. So yeah, probability 1/2, and then the probability that z equals 0 is also 1/2, right? So this reduced sample space only works because these coin flips are independent. If they're not, then I would not be able to take that shortcut. I would have to look at the entire sample space. Okay, so now that we have those, now we can figure out all of these equations. Right, so I know the probability of y equals 1 and z equals 1. The probability of y equals 1 and z equals 1, that is, all three flips are equal, and the first flip was heads. Well, I didn't really write it out in all the details, but it just consists of this one outcome, right? That's the intersection of these two events. So that means the probability of this, it's a uniform probability, is the size of that outcome over the size of the sample space, and it's 1/8. And then the probability that y equals 1 is 1/4, right? Or 2/8, whatever, however you want to say it. And the probability that z equals 1 using sort of the formal method is 4/8 or 1/2. Okay, and if I multiply 1/4 times 1/2, I get 1/8. So this is 1/8. This is 1/4 times 1/2 is 1/8. So yeah, these two events are independent. Events y equals 1 and z equals 1 are independent. So 3 more to go. But again, they're sort of simple. There's a lot of symmetry. I guess I got rid of my animations on this, but that's fine. Y equals 1 and z equals 0. Again, this is probability 1/2. This is probability 1/4. If I look at the intersection, y equals 1 and z equals 0, this is as if I said the first flip is tails. So y equals 1 is all three flips are the same, and z equals 0 is that the first flip is tails. So I have this outcome. So yeah, then the probability is 1/8, size of the event over the size of the sample space. Y equals 1 is 1/4. Z equals, what did I do here? This should be z equals 0. Z equals 0 is 1/2. 1/2 times 1/4 is 1/8. The same as before. So these two events are independent. Okay, so 2 equations down, 2 to go. Equation 3, y equals 0 and z equals 1. Well, yeah, if I look at the intersection, it's not the case that all three flips are equal. It is the case that the first flip is heads. And I can just, using inspection on my sample space, I can see that there are 3 outcomes that match that description. And so the probability of this event is 3/8. The probability that y equals 0, again, because there's only 2, I can use the complement rule. 1 minus the probability that y equals 1, or 3/4. And my event z equals 1 is, of course, 1/2. So yeah, I have 3/8 on the left-hand side and 3/4 times 1/2 on the right-hand side. When I multiply those together, I get 3/8. So yes, these events are also independent. So yeah, one last equation to prove. Y equals 0, z equals 0. So yeah, not all the flips are equal, and the first flip is tails. That has a size of 3. So that is probability 3/8. And yeah, if I do, plug the values in again, I get 3/8 equals 3/8. So these are also independent. Okay. So I took my 2 random variables, y and z. They each defined 2 non-empty events. I took all of the combinations of those events. There were 4 of them. And for all of the combinations, I showed that these equations held, which means that X and Y are independent, or sorry, Y and Z are independent. Okay, and that kind of makes sense, right? If I tell you Y equals 1, and then I ask you, well, is the first flip heads or tails? I tell you all the flips are the same, and I say, well, is the first flip heads or tails? And you say, well, I don't know, right? I mean, that gives you no information about the first flip. Likewise, I tell you that the first flip is heads, and then I ask you, do you think all 3 flips are equal? And I mean, there's no way of knowing, right? There's no way of knowing beyond what you already know, what the probabilities are. All right, questions? Okay. Are X and Z independent? We could try and show it. Or we can find a counterexample. So what might be a counterexample? So X is the number of heads in 3 flips. If I tell you the first flip is heads, I tell you the first flip is heads, that means X can be 1, X can be 2, X can be 3, but X can't be 0, right? So, yeah. If X is 0, then Z must be 0 as well. If I tell you there's none of the coins came up heads, that means they all came up tails, right? This corresponds to tails, tails, tails. Then I look at Z, Z cannot be 1. It can't be that the first flip is heads. It has to be that the first flip was tails. So given that, we can define an intersection of 2 events that's empty. So if X is equal to 0, that is there are no heads, and Z equals 1, that is the first flip is heads. There are no outcomes that match that description. So that's the empty set. That means the probability of the intersection of these 2 events is 0. And since these are non-empty sets, we know that these, as small as they might be, are not 0. And so the product is not 0. So yeah, we get the fact that these are X and Z are not independent. We could think about it a little bit and figure out why, but yeah. Okay, questions? Okay, so often when we talk about random variables, we talk about distribution functions. This is just the definition, there's no proofs in this. But in case you see the words distribution function, you will know what they mean. All it is basically well, let's see here. Yeah. So if I roll 2 dice is my experiment, and my random variable X is the sum of my 2 dice, the red and the blue die in this case, then the listing of all of the events and their probability is the distribution function. And so this is, formally this is correct, but you would often see it drawn as, right, if I had a probability on the left-hand side is 0 and 1, and then I have my X equals 2, X equals 3, X equals 4 along the X-axis, then, my probability function looks something like that. So yeah, that's what we mean when we say probability function is simply a mapping of all of the non-empty events for a given random variable to their probabilities. Questions? Okay. All right. So yeah, this is tedious but short. We're going to look at one more thing, but there is a lot of symmetry in this. So I'm going to take three random variables. So we saw we had X, Y, and Z earlier, and Y and Z were independent, but X and Z were not, or sorry, X and Z and X and Y were not. If I have three random variables, that was, what we described earlier was sort of, they were pairwise independent. But if you remember, if we have three or more events, we can talk about them being pairwise independent, but we can also talk about them being mutually independent. Okay, so if I have three random variables, then I get the same thing applying. So if I wanted to show that these three random variables were mutually independent, then I would have to show that X and Y were pairwise independent, Y and Z were pairwise independent, and X and Z were pairwise independent. And then I'd have to show that all three were mutually independent or three-wise independent by looking at all combinations of those, right? So yeah, we would have to verify equations that look like this, but it would have to do it for all possible values, X, Y, and Z. In this case, there's two each, so there would be 8 variations of that. All right, questions? I don't know if we should go through that or not. This is I mean, again, not the most exciting stuff, but it leads into some exciting stuff. Go through this. Okay. Well, let's try it. And then, so again, as promised, there's a lot of symmetry, so most of it should go pretty quick. And then we'll move on to some other, we'll take a bit of a break from the hard stuff and go to some easier stuff. But okay, so I have a sample space S, and it consists of the values 2, 3, 5, and 30. And these are all 2, 3, and 5 are prime numbers. Of course, 30 is divisible by 2 and 3 and 5. Okay, and in fact, 2 times 3 times 5 is equal to 30. So I'm going to define, this is a uniform sample space, right? So we're going to choose some outcome uniformly at random from those 4. And then we're going to define 3 random variables, X, Y, and Z. X is equal to 1 if our outcome is divisible by 2 and 0 otherwise. Y is equal to 1 if the outcome is divisible by 3 and 0 otherwise. And Z is equal to 1 if the outcome is divisible by 5 and 0 otherwise. Okay, so we can look at, let's define their probabilities, and then very quickly go through and show that, prove or disprove that these are mutually independent. So the probability X equals 0 is the probability that the value selected from S is not divisible by 2, and that is only possible if it's a 3 or a 5. So this is 3 over 5, the size, over the size of the sample space S, which is 2 over 4, or 1/2. Okay, so that's a probability that X is equal to 0. Everybody see that question so far? Okay, so I'm just going to list that as 1/2. Of course, then the probability that X equals 1 is also 1/2, right? Using the complement rule. For Y, if Y is equal to 1, then X is divisible, Then our outcome is divisible by 3. Well, this is divisible by 3. This is divisible by 3. These two are not, which means that half of them are divisible by 3. So similarly, we have probability that y equals 0 is 1/2. And the probability that y equals 1 is also 1/2. And the same is true for z, right? Which ones are divisible by 5? Well, 5 and 30. And the ones that are not are 2 and 3. Okay, so the probability that z equals 0 and z equals 1 are also 1/2. Okay, so we have all of our individual probabilities. And to prove pairwise independence of x, y, and z, we have to look at, well, we have to look at all combinations. And I'm just going to write we have to look at this probability, right? So for pairwise independence, we have to show, prove or disprove something like this. All right, so we're going to take the intersection of two events on the left-hand side, and we're going to multiply their individual probabilities on the right-hand side. Luckily, we have a lot of symmetry, right? So all of the individual probabilities are 1/2. Okay, so whatever's on the right-hand side is equal to 1/4, right? 1/2 times 1/2 is equal to 1/4. So yes, we have a bunch of these to prove, but the right-hand side's already taken care of, right? So we're just going to look at the left-hand side of all of these possible equations for pairwise independence. Okay. 2, 3, 5, and 30. And yeah, I just want a quick reference here. X div by 2, y div by 3, and z div by 5. Okay. So the probability that x equals 0 and y equals 0 means what is the probability that my number is not divisible by 2 and not divisible by 3? And out of these possible, only 5 falls into that category, right? 2 is divisible by 2. Yeah. And not divisible by 3, yeah. So 2 is divisible by 2, 3 is divisible by 3, 30 is divisible by both. So this is the size of this event over the size of S, and that's 1/4. Okay, so x equals 0 and y equals 0 is independent because we know that the right-hand side is also equal to 1/4. Okay. All right, so let's, now that, any questions? We're gonna start moving quickly through them now. Now that we have the hang of it. So the probability that x equals 1 and y equals 0. So now it's the number is divisible by 2 and not divisible by 3. So 30 is divisible by 3, so it doesn't count. Is divisible by 2. And not. Yeah, so that is just 2, right? 2 and, or is it 2 and 5? So all the ones that are not divisible by 3 are 2 and 5. But it is, yeah, so this is, sorry. This is only 2. So it has to be divisible by 2, which means 2 and 30. But it also cannot be divisible by 3, which eliminates 30. Right, so this is 2 over the size of the sample space, which is 1/4. Probability x equals 1 and y equals 1. So it's divisible by 2 and divisible by 3. That is only 30. So that's 1 out of 4. Probability that, so far, I've looked at 4 equations, x and y, all of their possible values. So x and y are independent, right? So now I just have to look at y and z and x and z. X equals 0 and z equals 0. So I need a number that's not divisible by 2 and not divisible by 5. That leaves only 3, right? Because 30 is divisible by everything. So this is 1/4. And then the probability that x equals 1 and z equals 0. So it's divisible by 2, but it's not divisible by 5. So that leaves only 2. So that's also 1/4. And so on and so on. So there are 8 equations. And if I asked you to prove this, you should do it. But at some point, you can recognize by symmetry that all of these cases are the same. So what does that mean? That means that x, y, and z are all pairwise independent. All right, that's a lot of questions. Okay, so now I want to prove or disprove that they're mutually independent. So I want to look at, for instance, x equals 0 and y equals 0 and z equals 0. And again, if I wanted to disprove it, I need a counterexample. If I wanted to prove it, then I have to show for 8 more equations that this is true. Whoops. Okay, but so yeah, this I know is non-zero. It would be nice if I could find one of these that is equal to 0. So this is the event that some number is not divisible by 2, and it's not divisible by 3, and it's not divisible by 5. And if I look at my set S, not divisible by 2, that eliminates these. Not divisible by 3, that eliminates 3. And not divisible by 5, that eliminates 5. So it turns out the very first one that we looked at was empty, which means that this probability is equal to 0, and it's not equal to whatever this happens to be. So x, y, and z are pairwise independent, but they are not mutually independent. Okay. Questions? I know it's a lot. It's a lot of rote mathematics this morning. So yeah, my apologies, but it does get more interesting in the coming lectures. All right, I think we did enough independence. Yeah, so let's go back. We still got quite a bit of time left, but let's sort of look at some easier questions and maybe review a few concepts from earlier. I like this question because this is a tripping point for a lot of people when they do their assignments. So let A and B be 2 events in some probability space such that the probability of A is equal to 2/5 and the probability of not A union B is equal to 3/10. So assume that A and B are disjoint, determine the probability of B, and assume that A and B are independent, and determine the probability of B. Okay, so first of all, what does it mean if they're disjoint? Let's do the first one. That means they have no outcomes in common. Okay, so at some point we're going to use that fact. We have the probability of A is equal to 2/5 and the probability of A, this thing. Okay, so these are sets. I don't want to compute this. I want to break it down a little bit more. I want to use De Morgan's law here. Possibly, we'll see. Actually, yeah. If I use De Morgan's law, then I can say this is equal to the probability of A naught intersect B naught. Okay. So A naught intersect B naught is, if I look at my Venn diagram, what is that? So A naught is everything outside of A. So let me draw a couple diagrams that I can mess up. So what is A naught? Well, A naught is everything outside of A, including B. All right, and then B naught is everything outside of B, including A. So if I take the intersection of the complement of A and the complement of B, so I want everything that appears in both of these. Then if I draw another diagram, everything that's in common in both of those diagrams is everything outside of A and B. Right, so this is the intersection of A naught and B naught. Okay, so I know probability of, so I know the probability of this is 3/10. And I know the probability of A is 2/5. Okay, and I want the probability of B. So how do I get it? Yeah. Could I? Bayes theorem? Perhaps. Those might work. That's not really what I had in mind, though. I think we can do something a lot simpler. Because, well, what is it about? We know A and B are disjoint. What about A naught intersect B naught? Is that just does that intersect A or B? I mean, no, right? So I have three sets or events, A, B, and A naught intersect B naught. And they are all disjoint. And if I take the union of them, what do I get? Yeah. Yeah, so they are disjoint and they together they completely describe the sample space. So they have a probability of 1. And since they are disjoint, I can write this as probability of A plus the probability of B plus the probability of A naught intersect B naught is equal to 1. And now I have 3 terms and I know 2 of them. So I have probability of B is equal to, well, I'm going to subtract the probability of A and the probability of A naught, B naught from both sides. So I get 1 minus 2/5 minus 3/10. And what is that? So I think that's 3/10. If my grade school math is correct, which it often is not. So yeah, if they're disjoint, we know that these three things, I've been given two of them, and ask for a third, they're disjoint, and the union is the sample space, which means I can just use all three probabilities added together should equal 1, and I can work backwards from there. Question? Okay, let's look at see if I can copy this or something. Bunch of other stuff possibly look at. Okay, so now let's assume that they are independent. So now what does my Venn diagram look like if they're independent? Well, in this case, yeah, now we probably want to use, well, we know a couple things, right? Let's write what we know. A intersect B equals probability of A times the probability of B. That might come in handy. But what else do we know? We know that this, using De Morgan's law, we know that this is equal to probability of A naught intersect B naught, right? I negate each individual term and I flip my union to an intersection. Yeah. So it's not true that A or B happened is the same as saying A did not happen and B did not happen. Okay, so what is, but what can I say about this now? A and B are independent. Independent tells us this. But if I know that A and B are independent, what do I know about A complement and B complement? Right? They're also independent, right? So if these are independent, then I can also write this as probability of A complement times the probability of B complement. Okay, and I don't know B complement or A complement probabilities, or do I? What's the probability of A complement? Yeah. Yeah, it's 3/5. It's simply 1 minus the probability of A, which is 1 minus 2/5, which is 3/5. And I know that probability of B complement is, I don't know the value, but I know I can write it in terms of probability of B. So this I know is 3/10. So I can say 3/10 is equal to 3/5. And then the probability of B complement is 1 minus the probability of B. Okay. And now I'm going to just distribute the 3/5. And let's see, what do I get here? That's a minus. Good grief. So 3/5 probability of B equals 3/5 minus 3/10. I hopefully didn't make any mistake there. But yeah, I just distributed 3/5 over these two. I moved the negative 3/5 probability of B to the left-hand side, and I moved the 3/10 to the right-hand side. And then that is 3/5 minus 3/10 is what, 6/10 minus 3/10. So 3/5 probability B equals 3/10. Right, so this is 6/10 minus 3/10, which is 3/10. And then probability of B, I can multiply both sides times 5/3. And I get, this cancels with this, I get 5/10, which is equal to 1/2. Okay. So yeah, that's questions. Okay, so yeah, that is, and yeah, that is the difference, you know, operationally between disjoint and independent, I suppose. But all right, we have 10 minutes. Let's see what other thing we can do. Oh, total law of probability. Yeah. So this is technically what you would use for the, so the first assignment question is infinite sample spaces, and part of it uses this law of total probability. I did sort of give you an in the lecture an informal way to do it, which is in the slides. This is technically the way you would, if you want to be really formal, I'm okay with the informal method, right? Where we know that if I break my string into 2 independent substrings, that those are, the probabilities are determined independently, and this one only happens if this one happens, but yeah. And, yeah, I don't know. None of these are particularly interesting. But let's do a uniform sample space before we go, just for fun. So we're going to analyze, so in algorithms, these types of things come up in algorithms that are random, right? Because potentially, if I have something like this, it could loop forever, potentially. Now, it's not going to, because in real life, random algorithms perform surprisingly well, right? It's surprising what things you can determine really quickly using randomness, and where all of these deterministic algorithms kind of take a long time. So get random bit, I have a coin that I don't know if it's fair, right? So I have a coin and it has heads and tails, but it's a little bent. Maybe it comes up heads more often or tails more often. And I don't know exactly the probability, but I do know there is a probability that it comes up heads. We'll call that probability P. And tails, of course, since there's only 2 outcomes, must come up with probability 1 minus P. Okay, so these are the complement of each other. And I want to use this biased coin to get a completely random flip, or a fair flip, right? So I'm going to run this algorithm where I'm going to flip my coin twice. And if the result is heads, tails, I'm going to return a 0, right? So this bit, what I really want is I want a fair coin. I flip it. If it comes up heads, I say 1. If it comes up tails, I say 0. And that has probability 1/2. But in this case, my coin is bent. Maybe it's not fair, but I'm still going to use it to get a bit. I'm going to get 1 with probability 1/2 and 0 with probability 1/2 by flipping this coin. So the algorithm is I flip the coin twice, and if the result is heads, tails, then I return a 0. I'm done. If the result is tails, heads, then I return a 1 and I'm done. Otherwise, I run my algorithm again. I flip my coin twice again. Okay. So everybody clear on the problem that we're solving? And we're going to prove that this now, I get a 1 with probability 1/2 and a 0 with probability 1/2 using these infinite sample spaces. So if I look at the outcomes, yeah, so heads, tails. This comes up heads with probability P and tails with probability 1 minus P. Each coin flip is independent, so I can take the product of the two probabilities, right? So it's P times 1 minus P. Likewise, the probability of tails heads, right? So this is I return a 1, this is I return a 0. It's equal to 1 minus P times P, but I can rearrange the terms. These have the same probability. Okay. And then I have probability heads heads is equal to P squared, and the probability tails tails is equal to 1 minus P squared. Okay, so I perform this experiment until one of these two outcomes happens. And this is the probability that I keep going. So any event in my sample space is going to look something like this. I'm going to get heads heads or tails tails some number of times, followed by heads tails, right? So I want to find the probability that I'm going to return a 0. So the outcomes that map to returning a 0 all look like this. Okay, so I don't, right, does that make sense? Similar to what we did last class. So now I want the probability of these things. Well, the probability that I roll heads, flip heads heads or tails tails. Heads heads is P squared, tails tails is 1 minus P squared. These are disjoint, so I'm going to use the sum rule. So this is, yeah. Yeah, so this is equal to the probability that I get heads heads or tails tails to the power n times the probability that I get heads tails. And then this is equal to P squared plus 1 minus P squared to the power n times P times 1 minus P. How am I doing for time? 3 minutes, should be able to. Okay, so this is all my probability that I get 0. So now, or this is an individual outcome, and now I'm going to sum them all up to get my event that I return a 0 bit. Okay, so the probability that I return a 0 equals n equals 0 to infinity, P squared plus 1 minus P squared to the power n times P 1 minus P. Okay, P 1 minus P does not depend on n, so I could take that out. P times 1 minus P. And so now I have a closed form for this. Of course, this is my x. So it's 1 over 1 minus x, and I get, and I'm moving a little fast here, but 1 over 1 minus P squared plus 1 minus P squared. Okay, and then using a little bit of algebra, I get this over, yeah, sorry that I'm sort of intruding on this other part. 1 minus P squared, I'm going to expand this part out. I have P squared minus 2P plus 1. And so that is equal to P over 1 minus P What do I get? 2p minus 2p squared. Okay. And then if I expand that out, I get p minus p squared over 2p minus 2p squared. That is simply 1/2, right? I can factor out the 2 and the p minus p squared cancels out and I'm left with 1/2. Sorry, kind of rushed a little bit at the end. It is rather, so even though this looks kind of ugly compared to what we've looked at before, the process is still really simple, right? This is, I'm going to do the 1/1 minus x closed form where x is equal to this. And then after that, it's all just algebra. But yeah. So yeah, that's it for today. I guess that's it for this week. I have office hours tomorrow at 10 if anyone needs help. Otherwise, I'll see you guys next week.